So I am live right now. Oh shit. Let's see here. So this is back up. It's the same one. So this is back up. It's the same one. Yo, is this echoing? Is this live? Let me know. There's 4 people watching, so clearly you're a creep if you're not going to tell me.
Waves. And the classical notion of what a wave is, it's the disturbance traveling through a medium. Disturbance traveling through a medium. So what do we mean by disturbance, and what do we mean by medium? Well, we can come up with some fairly simple examples. Let's say that I have a little puddle here. So that's my little puddle. And let's say I want to drop a stone in.
So is that echoing? Little echo? Alright, I gotta figure this out. So if this
puddle. So this is my stone.
This is going
puddle, and we've all seen what happens. Right when it goes into the water, that pushes that water down, pushes the water around it.
Oh, okay, maybe I go this.
Back up, and then you have this traveling disturbance. You have this traveling disturbance. These kind of rings start to radiate outward from
1 second.
From where I actually draw.
1 sec, let me figure this out.
So you go to sound, or in your control panel, you can find it in your start menu. Go to sound, go to recording, and this is my headset with my microphone, and this is my computer.
What?
So your desktop audio in OBS that records your gameplay audio was also picking up my voice. So it was picking up my voice here, and it was also picking up my voice here. So to make it stop doing that, you right-click it, properties. You want to go to levels and turn both microphones down to 0. This was at 20, this was at 93. And then you hit apply, and okay. And when I tap on where my microphone is on my computer, no more sound comes out. So when you record, you shouldn't be hearing your double voice anymore.
Dropped the pebble, and you can actually see them. You can actually see them move outwards. You can see the crests of those waves move outwards. So we're talking about a disturbance. Well, this is that disturbance. The pond was completely flat, but then we agitated. We pushed it down. It pushed the water outwards, and then that pushed the water next to it up and down, and it traveled outwards from the point of that initial disturbance. So we have this disturbance traveling through the medium. What's the medium here? Well, the medium here is the water. And the disturbance, the initial disturbance, was the rock disturbing that water, but then that water disturbed the water around it, which disturbed the water around it, so that disturbance kept traveling through the medium. And we can give other examples of this. If I take let's say if I were to take a really long string and hold it right there, and that's my hand. So the string is, let's say it's just attached to something. So let's say it's a really long string, and right now there's some slack in it. It's attached to a wall. And let's say that I were to if I take let's say if I were to take a really long string and hold it right there, and that's my hand. So the string is, let's say it's just attached to something. So let's say it's a really long string, and right now there's some slack in it. It's attached to a wall. And let's say that I were to start moving my hand up and down. So I move my hand up and down. What's going to happen? Well, if I just did, let's just think about if I just did it once. If I just did it once, what I'm going to have is this lump of string move from the left to the right. So that's what it's going to look like at first. Then a few seconds later, it's going to look like this. It's going to look something like this. And you're going to have this disturbance, which is this wave, this lump that I just generated. It is going to move. It is going to move to the right. What's the medium? The medium in this case is the string. It is the string. And what just happened there? Well, when I jerk the string up, I'm disturbing those string molecules right next to my hand, and they're pulling on the string molecules next to them, pulling on the string molecules next to them, and so then you have this traveling lump. So once again, these are both examples of waves, disturbances traveling through a medium. Now I can give through a medium. I can give other examples. Sound waves. What causes sound waves? Well, you have a bunch of air particles all bouncing around at actually surprisingly fast speeds. But if you disturb them, if you cause something to, say, compress a bunch of air particles right here, so these air particles get ultra compressed, some type of clap happens, so these get ultra compressed, well, then they're going to bounce on the ones next to them. And so once again, you have this disturbance traveling through the medium. In this case, the medium is the air. The medium is the air. So now that we've seen some classical notions of waves, let's think about something a little bit more mysterious, and that is the notion of light. We do believe light definitely has wave-like properties. Light can interfere with each other, and we could do a whole other videos on light. If I were to take a barrier like that with two small slits in it, and if I were to shine some light, one way to think about it is these slits are the only place where the disturbance gets through, and then it would cause the light to propagate from each of them like that. And maybe I'm just drawing the crests of the waves, but it also come out from here. And so you can see where the two crests meet, they're going to constructively enhance each other. They're going to constructively interfere. And if you were to put some type of detector, right over here, you would see the bright points of the light, and you would see the dark points of the light. So light definitely behaves like a wave. I'm just showing even just one example of light behaving like a wave. But if it is a wave, well, that means it needs to be, or if we use our classical logic, you would say, well, that means it's a disturbance traveling through a medium. But what is that medium? We have light coming from our sun. We call it sunlight. We have light coming. I keep wanting to make it actually our sun is white. We tend to draw it as a yellowish color, but that's just because of what happens as it goes through the atmosphere. So you have the sun, you have the earth. This is not drawn to scale, and somehow that light is able to reach us over 93 million miles. Over 93 million miles. What's it going through? Is it a disturbance traveling through a medium? Well, for a long time, people said, well, it must be. It has these wave-like properties. It seems to be traveling with a velocity, the speed of light. So there must be a medium that it is traveling through. And people theorized what this medium is. They called it the luminiferous ether. Let me write that down. It's a fun word. It's a good name for a band. Luminiferous, now I'm not spelling it right. Luminiferous ether. And there was this idea that maybe even in the vacuum of space, you have this substance, this luminiferous ether that the light is traveling through, that it's somehow it's a disturbance in that luminiferous ether. Now, what we're going to do in future videos is we're going to test that. We're going to see if that's actually the case, because what's interesting about if there is a luminiferous ether, well, we're not going to be stationary relative to that luminiferous ether. In fact, we're orbiting around the sun. The sun is orbiting around the center of the galaxy. There's no way that we're going to be stationary relative to that luminiferous ether. So if we're not stationary relative to that luminiferous ether, we should be able to detect how light behaves if it's going kind of in the direction of ether, or if it's going against the direction of the relative movement of the ether relative to us. So anyway, I'll leave you there. This mystery of science. Waves, disturbance through a medium. We saw that with the water, with the air, with the string. But what about light? Is there a luminiferous ether? Put a question mark there.
Okay. Greetings, cowboys and cowgirls. What's up? How you doing? How you doing? The ether. This is like screaming out Satan in the middle of a church. When you're talking to modern academic scientists who are not scientists by definition and denotation, what they are mathematicians, i.e. atomists. The most evil word is the word ether. Now, when it comes to Mother Nature, and of course Mother Nature is not a person, we're talking about natura naturans, right? Mother Nature doesn't give a crap if you call it zero-point energy or the ether or counter space or a non-Cartesian inertia. The original definition of inertia, not the current connotation of inertia. The ether is absolutely undeniable. Interesting little experiment that you could do, right? Mother Nature doesn't give a crap if you call it zero-point energy or the ether or counter space or a non-Cartesian inertia. The original definition of inertia, not the current connotation of inertia. The ether is absolutely undeniable. Interesting little experiment that you could do. I was trying to think, you know, like without having a bunch of equipment as far as proving the ether, what's the most simple way to prove the ether? Like you could have like a little bar bet. Okay, but your buddies would actually have to look up the complex, or not that complex, equations for calculating magnetic field strength and its variance at distance. In other words, how far you get away from a magnet, right? Right? Now let's just say we were in outer space. A vacuum, outer space is not a complete and total vacuum, but we don't even have the air to contend with, no oxygen and nitrogen molecules. So let's just say this experiment is done in outer space. Well, we could do this on Earth, obviously so. All you need is a decently large magnet, like a 2-inch by 2-inch by 1-inch. You can get those for $40 now. Neodymium iron boron, N50 Gauss is a block magnet. I got a pile of them. They're really dangerous. They're so much fun to experiment with. And like an old tube TV set, you know the type, just turn it to a black channel or a white channel or a static channel. Okay, you could step the hell back up about 20 feet. But let's first start off by saying something here. Speaking of magnetic field intensity, how it varies with distance, we're talking about like the maximum distance on that 2-inch by 2-inch by 1-inch as measured in inches, okay? In other words, how much influence we've got is about yay far. If you actually apply the calculation for magnetic field influence, okay, or strength at distance, we're talking about yay far, right? Okay, so that's the maximum distance which we have the ability to have a variance, like in a Gauss meter, of influence of static field. Now, an active field, of course, is in relationship to Maxwellian field equations, output over a given period of time in a known vector. Of course, the output would be joules, watts, volts, so on and so forth. Maxwellian field equations, of course, never define a field. The interesting thing about the ether, however, and I'm going to get to the experiment very, very quickly here, is that modern physicists also admit to the ether. However, it's the most evil word to them. They absolutely deny it outright. With the Michelson-Morley experiment, never denied the ether. It's a completely absurd experiment. Absolutely as absurd as the Schrodinger's cat thought experiment. A completely baseless and groundless nonsense. But anyway, supposedly Michelson-Morley experiment refuted the ether, but of course it did no such thing. But modern scientists actually who cannot reconcile EPR, look up EPR if you like, or instantaneous action at a distance, they still admit to the ether, except they actually hide it in euphemisms. They call it quantum foam or quantum fluid, or there's about 6 different things that modern quantum and the physicists actually refer to the ether with yay far. If you actually apply the calculation for magnetic field influence, okay, or strength at distance, we're talking about yay far, right? Okay, so that's the maximum distance which we have the ability to have a variance, like in a Gauss meter, of influence of static field. Now, an active field, of course, is in relationship to Maxwellian field equations, output over a given period of time in a known vector. Of course, the output would be joules, watts, volts, so on and so forth. Maxwellian field equations, of course, never define a field. The interesting thing about the ether, however, and I'm going to get to the experiment very, very quickly here, is that modern physicists also admit to the ether. However, it's the most evil word to them. They absolutely deny it outright. With the Michelson-Morley experiment, never denied the ether. It's a completely absurd experiment. Absolutely as absurd as the Schrodinger's cat thought experiment. A completely baseless and groundless nonsense. But anyway, supposedly Michelson-Morley experiment refuted the ether, but of course it did no such right. With the Michelson-Morley experiment, and I'm going to get to the experiment very, very quickly here, is that modern physicists also admit to the ether. However, it's the most evil word to them. They absolutely deny it outright. With the Michelson-Morley experiment, never denied the ether. It's a completely absurd experiment. Absolutely as absurd as the Schrodinger's cat thought experiment. A completely baseless and groundless nonsense. Word to them, they absolutely deny it outright. With the Michelson-Morley experiment, never denied the ether. It's a completely absurd experiment. Absolutely as absurd as the Schrodinger's cat thought experiment. A completely baseless and groundless nonsense. But anyway, supposedly Michelson-Morley experiment refuted the ether, but of course it did no such thing. But modern scientists actually who cannot reconcile EPR, look up EPR if you like, or instantaneous action at a distance, they still admit to the ether, except they actually hide it. Morley experiment refuted the ether, but of course it did no such thing. But modern scientists actually who cannot reconcile EPR, look up EPR if you like, or instantaneous action at a distance, they still admit to the ether, except they actually hide it. Scientists actually who cannot reconcile EPR, look up EPR if you like, or instantaneous action at a distance, they still admit to the ether, except they actually hide it in euphemisms. They call it quantum foam or quantum fluid, or there's about 6 different things that modern quantum and physicists actually refer to the ether without using the word ether, because the ether is literally the big evil Satan/devil word. And so you just don't say that stuff. You just don't speak the word Satan, in the middle of church, right? It's the same thing with the word ether. Its connotations are literally that deep. And of course, there's been 1,000 different philosophies and metaphysics on the ether dating back to the ancient Greeks and even further. But the ether is, of course, ever present and undeniable. Now to the experiment. All you have to do is have a tube TV set, old tube TV set, and one of those little 2-inch magnets, or even one larger than that. Now we know that a given magnetic influence with distance, you've only got influence about that far. That's off a static field. All you actually have to do is sit there and wave that magnet 2 inches or larger at 20 feet plus. If you actually have a little spotting scope at say 30 feet plus or even 40 feet, you can still see the influence. You can actually get back with a spotting scope, since you can't see the TV set at 40 plus feet, not in really fine detail like I get my eye up against this computer screen, but 40, 50 feet back with a spotting scope, okay? You can wave that magnet just like this, and that you will actually see influence. Now, of course, the TV tube is nothing other than an electrostatic generator. Okay, so then a vacuum tube striking a RGB array, depends on which type it is. We're just talking about an old tube Sony or some old tube TV set, which you probably have one in your basement. Most people have thrown them away now. If you ever want to have a bet with somebody, say, let's just go off the known calculations for magnetic influence with distance. It falls off completely as palpably measurable about yay far. I said, what if I could actually cause a magnetic influence and prove the ether? And if you're able to go into space in a total vacuum, someone would say, well, this is the influence of the magnet upon the air molecules, the oxygen and nitrogen, and it's transferring. That's not what's happening. But even if you were to go in a total vacuum out into space with a tube TV set and you in your space suit, you would still see the exact same influence. You'd actually see it more because you'd have no influence of the dielectric permittivity and the magnetic permeability of the nitrogen and oxygen separating between you and the tube TV set. What this does when you're actually waving the magnet is you're setting up a field perturbation and a strain in the hysteresis of the ether. Let me repeat that very succinctly, okay? Not using gobbledygook words here. You're setting up a strain in the hysteresis and the stasis of the ether. No different than a little bitty person. Well, what sort of influence does a little child have in the middle of a pool? How much influence? Because a little child's arms are about yay long, right? Right? How much of an influence could a child have in the middle of a pool, flapping his arms? Of course, the water would be analogous to the ether. Well, quite a long way if you actually had the hysteresis of the ether, in this case the calm waters of a large Olympic-sized swimming pool. You know, a little child could flap his arms and create little waves against the edges of the pool, 50, 100 feet out, right? Even further. You could actually back up. Of course, you'd have to step outside of your house or put the TV set down the end of the street, okay? You can, as far as I've seen, it has been 80 plus feet. You have to have a little spotting scope or pair of binoculars, right? Sure, you got a pair of binoculars. Put it down the street, okay? Take the binoculars up to your eyes. Do this with the magnet, right? You will see the influence on that electrostatic, dielectric, electrostatic, same thing, projection on the phosphorus-coated screen of that old tube TV set, from 50, 60, 80 feet away. If you want to stick the TV set down at the end of the street, your neighbors might look at you like you're a nut job. But, this runs contrary to what science says about the influence of distance of a given Gaussian flux magnet. It's both its volume and what it's rated at in a Gauss meter. So, well, this magnet is, 0.4 Tesla, and it has a volume of 40 square centimeters. Actually, that's not the volume of a 2 by 2 by 1 inch. Point being is that the ether does exist. I'm trying to think of a really simple experiment that you could use to prove to people. With the known given math of magnetic field influence, this, of course, is not possible. But science doesn't admit to the ether, but the ether is, everything is the ether. Absolutely everything is the ether is undeniable. Trying to deny the ether is like trying to enjoin a self-negation paradox, because subject precedes the object of negation, and denying the ether is absolutely ridiculous. Because science itself has never defined a field. Maxwellian field equations, for example, only define a field over a vector with a period of time with a given result. Maxwellian field equations never define a field itself, in itself, by itself. What is a field? Ancient Greek word kora. Modern science has never defined a field. Never. You will find no definition of a field anywhere. Go to Wikipedia, go anywhere. Just find a definition of field. The answer for what a field is very simplex. It's an ether perturbation, which takes on 4 different modalities, depending on how you look at it. We have gravity, electricity, magnetism, dielectricity. Of course, there are really only 2 fields. There's dielectric and magnetic, and ultimately that's reducible to 1, because magnetism is the extrapolation of the dielectric field with the loss of inertia, as manifested. The answer for what a field is very simplex. It's an ether perturbation, which takes on 4 different modalities, depending on how you look at it. We have gravity, electricity. Very simplex. It's an ether perturbation, which takes on 4 different modalities, depending on how you look at it. We have gravity, electricity, magnetism, dielectricity. Of course, there are really only 2 fields. There's dielectric and magnetic, and ultimately that's reducible to 1, because magnetism is the extrapolation of the dielectric field with the loss of inertia, as manifests as force and motion. Centrifugal divergence, i.e. force and motion. Of course, the dielectric is counterspatial. Magnetism is spatial. 100% of the universe only perturbation. Ancient Greek word kora. Modern science has never defined a field. Never. You will find no definition of a field anywhere. Go to Wikipedia, go anywhere. Just find a definition of field. The answer for what a field is very simplex. It's an ether perturbation, which takes on 4 different modalities, depending on how you look at it. We have gravity, electricity, magnetism, dielectricity. Of course, there are really only 2 fields. There's dielectric and magnetic, and ultimately that's reducible to 1, because magnetism is the extrapolation of the dielectric field with the loss of inertia, as manifests as force and motion. Centrifugal divergence, i.e. force and motion. Of course, the dielectric is counterspatial. Magnetism is spatial. 100% of the universe only has volume due to magnetism and magnetism only. The ether is an absolute. The ether is undeniable. Even the idiot scumbags of quantum mechanics believe in the ether, but they don't use the word ether. They call it quantum fluid. I can't remember the 4 other names that they use, but they still admit to the ether, because you can't explain the universe with bumping particles. It's absolutely impossible. The only thing that can explain, like light slowing down, of course light doesn't move at all, it's a rate of induction, and speeding back up without breaking the law of conservation of energy after leaving glass or water, is ether. Everything is capacitance, resistance, magnetic permeability, and dielectric permittivity. You can't explain these things with damn particles. The universe is not bumping particles. That's why I call quantum the cult of bumping particles. When you deny the ether, okay, and modern physics is only a theory, when you deny the ether, then you must replace it with something else, and that's something that it has been replaced with. It's not my opinion, this is what they say, is bumping particles. It's the cult of bumping particles. The only problem with that is it's illogical, it's contradictory, it doesn't explain given phenomena. Only the ether explains that. Only the ether can explain not breaking the law of conservation of energy, of light speeding back up, and countless other phenomena, instantaneous action at a distance, electromagnetic retardation. That's what it's actually called. EMR, electromagnetic retardation. The universe is extremely simple, but it's not simplex. But the picture that's painted of cosmic mechanics by modern physics and quantum is illogical, absurd, and, you know, the brainchild of a bunch of atomistic, insane fools. The ether is undeniable. I guess that's the end of this video. There's a lot more I'd like to say, but I've been so damn busy today. I got like 10,000 things to do, and it's already 12 midnight. I never have enough time to do everything that I want to do. Thank you, and goodbye.
So let's think a little. We've already talked about light having wave-like properties, and the waves that we're familiar with in our everyday life we consider to be disturbances traveling through a medium. We talked about dropping a pebble in water, and the water is the medium, and we see the wave travel outwards. We think about sound waves, which is a disturbance in the air. We think about a wave traveling through this rope. The medium there is the rope. So in the mid-19th century, it was completely reasonable for folks to say, well, look, light has wave-like properties. It must be a disturbance traveling through a medium. And they said, well, what do we call that medium, even though we don't observe it directly? Well, let's call it the luminiferous ether. So an obvious question that was facing folks who had this reasonable assumption, they said, well, can we somehow detect the luminiferous ether? Can we validate the luminiferous ether existing? And a key realization is, well, we must be moving quite rapidly relative to the luminiferous ether. How do we know that? Well, we just have to remind ourselves that obviously the Earth is rotating, but not only is it rotating on its own axis, but it's rotating around the sun. And so if this is the sun right over here, this is the Earth. The Earth is rotating, and these are all rough figures. The Earth is moving around the sun at approximately 30 kilometers per second. 30 kilometers per second. By our everyday standards, that's quite fast, but we're not done yet, because the sun is also moving around the center of the galaxy. And this isn't an actual picture of the Milky Way. Obviously, we haven't gotten this far from our own galaxy to actually get this type of a vantage point. But if the sun were right over there, the sun, estimates are moving with a speed of roughly 200 let me write that in a better color so you can actually see it. 200 kilometers per second. 200 kilometers per second around the center of the Milky Way. And then the Milky Way itself could be moving. So we don't know our actual our orientation relative to the ether, but we're constantly changing our orientation. We're moving in these orbital patterns. If there is some type of luminiferous ether, and I'm just going to draw these lines over here. kind of show our luminiferous ether, we must be moving relative to it if we orient ourselves just the right way. In fact, the odds of us being stationary relative to the ether are pretty close to zero, especially if we wait a little. If we're stationary relative to the ether right now, let's say at this point, since we're changing our direction, we're not going to be stationary relative to the ether at that point. And that's just when you consider the Earth's orbit around the sun. It's even more true when you think about the solar system's orbit around the center of the galaxy, or even the movement of the galaxy. So we should be moving relative to the ether, or the ether should be moving relative to us. So we should be able to detect some type of what's called an ether wind, because it should be moving relative ether wind. Now, how would you detect an ether wind? Well, let's think about some other type of medium moving relative to us. Let's say that we are sitting on an island. Let's say that we are sitting on a, let me do this in a better color for an island. So let's say that we're in an island that's in the middle of a stream. So these are the shores of the stream. These are the shores of the stream, and there is some type of a current. So the water is moving in that direction. So that's the medium. And now let's start a wave propagating through this. So if I were to just take a pebble and drop it right over here, what would happen? Well, the wave is going to propagate faster to the left than it is to the right. And this is from our everyday experience, and that's because to the left, it's moving, the medium is also moving to the left. So as the medium moves and then you propagate through that medium, you're going to move faster to the left than to the right. So the wave is going to propagate something, so after a small period of time, the crest on the right might be there, but the crest on the left might be there. So it might look something like this. And then after another period of time, it might look something like this. So the general point is, for this little stream example, you're going to see your wave propagate faster in the direction of which the medium is moving. So similarly, if you have an ether wind, and this luminiferous ether is the medium by which the light propagates, the light is a disturbance in this medium, then if this ether wind has some, let's say it has some speed, well, let's just call it s, if you were to try to propagate light in that direction versus in this direction, it should go faster. We should notice it going faster if it's going along the same direction as the ether, because it's propagating through something that's also moving relative to us. And likewise, if it's going in the opposite direction of the ether, even though it's propagating through the actual ether at that same speed, the ether is moving in the other direction. So the light, based on our 19th century understanding of the universe, the light should seem slower. So you can imagine people started to theorize, well, maybe we can measure light in different directions and see if relative to us, we see a different velocity for light. Now, the problem is that in the mid-19th century, light is incredibly fast. We now know that the speed of light is approximately 300,000 kilometers per second. And in the mid-19th century, we didn't have good tools to measure this with a lot of accuracy, especially because the ether wind itself, even if you say, hey, this is 30 kilometers per second, maybe we're moving around the galaxy at 200 kilometers per second, maybe 300 kilometers per second, that's still a small fraction of the actual speed of light. So if you don't have a lot of accuracy when you're measuring the speed of light in these different directions, and the ether wind is so slow relative to the speed of light, well, with just traditional tools in the 19th century, you're not going to be able to detect this actual ether wind if it existed. And that's what gets us to the famous Michelson-Morley experiment, because there they didn't just directly try to measure the speed of light in one direction or another. Instead, they thought about, well, let's split some light into two different directions and then recombine them and see the interference patterns. And if the different directions traveled at different speeds, then we'll have different interference patterns. And we're going to see that in the next video. we've seen in several videos so far that most of the waves that humans have encountered in nature, waves in the water, sound waves, or just waves traveling along a rope, they were disturbances traveling through a medium. And so when light displays or has wave-like properties, a very natural assumption was, well, light must also be a disturbance traveling through some type of a medium, even if that medium wasn't so easy to detect. But they conjectured that there is some type of medium that light is a disturbance traveling through, and they called it the luminiferous ether. And much of physics in the 19th century was all around proving that the luminiferous ether existed, and also figuring out what our relative velocity was what our relative velocity was in regards to that luminiferous ether. And why do we feel confident, or why did they feel confident that there was a relative velocity? Well, we talked about that in the last video. The Earth is spinning, and then it's spinning around it's orbiting around the sun at a nice clip, and then the whole solar system is orbiting around the center of the galaxy at a nice clip. The galaxy itself might be moving. So if you have some absolute frame of reference that's defined by the ether, well, we are going to be moving relative to it. And if you said, okay, if we're moving relative to it, well, maybe you just measure the speed of light in different directions and see whether the speed of light is faster or slower in a certain direction. And then that might help you identify, well, one, validate that the ether exists, but also think about what our velocity is relative to the ether, relative to that absolute frame of reference. But the problem in the 19th century is that we did not have any precise way of actually measuring or a precise enough way of measuring the speed of light where we could detect the relative difference due to the light going for or against or into or away from the actual direction of the ether wind. And so the experiment that is usually cited with first kind of breaking things open and starting to really make a dent in this whole idea of a luminiferous ether is the Michelson-Morley experiment. Michelson-Morley experiment. They recognize, okay, we can't measure the speed of light with enough precision to detect has it gotten slowed down by the ether wind or sped up by the ether wind. But what we could do, and this is what Michelson and Morley did do, and I'm going to do a oversimplification of the experiment, and they said, okay, you have a light source. You have a light source right over here. So you have a light source, and so that's going to send light in this direction. It's going to send light just like that. And what you do is you have a half-silvered mirror that allows half the light to pass directly through it and half of it to be reflected. So let's put a half-silvered mirror right over here. So there's a half-silvered mirror. And so half of this light will bounce off like this. This is just a simplification of it. Let me do it a little neater than that. So half will bounce off like that, and then the other half will be able to go through it. We'll be able to go through it. It's a half-silvered mirror. And then we make each of those light rays, we've essentially taken our original light ray and split it into two. We'll then bounce those off mirrors. Bounce those off mirrors that are equidistant, and there are some adjustments when you actually have to factor in everything, but just as a simple notion, these things are just now going to bounce back. So this one is now going to bounce back. It's half-silvered. It can go through, or part of it can go through that mirror. So that's that ray. And then this one is going to bounce back. This one's going to go bounce back, and part of it is going to bounce into this direction. And then you can detect what you see. You can detect what you see. So this right over here is a detector. And you might be saying, okay, Sal, well, what's the big deal? You've taken a light source, you've split the light rays, you've put them back together, you've bounced them around a little bit. But think about if there was a luminiferous ether, these light waves that are going in orthogonal directions will be going at different velocities. Let's say if the ether wind was doing something like, let me see, if the ether wind were in this direction, if the ether wind were in that direction, when the light wave is going that way, it should be going faster, and when the light wave is coming back, it should be going slower. And so what Michelson and Morley did is okay, let's assume, let's adjust our apparatus right over here. So when these two light rays bounce off and then come back together, if there were no ether, you would have some basic interference pattern. So, and what do I mean by interference pattern? Well, let's say that you have maybe this one bouncing from up here. Let me do that in a different color. So the one bouncing from up here, let's say that that looks like this. I'll just draw it as a longitudinal wave, just like this. Best I hand-drawn longitudinal wave. And then the one coming from the other direction, the one that bounces here and then comes back like this, is another longitudinal wave like this. And when they overlap, they are going to interfere with each other, either constructively interfere or destructively interfere. So you could have something like this. So let me copy and then let me paste it. So depending on how far or how fast each of these traveled, you're going to have different levels of interference. And you would have a difference depending on the orientation, depending on what the actual ether wind is doing. But what Michelson and Morley observed is that no matter how they oriented this apparatus, and they did it at different times of the year, and they rotated around, and they rotated in the vertical direction, in the horizontal direction, no matter what they did, they always got the same interference pattern. The interference pattern did not change. And because the interference pattern did not change, it implied that, well, maybe this ether isn't really having an effect on slowing down or speeding up the light waves. So this is often called one of the most famous failed experiments in physics. So let me write this down. What's powerful about it is that it was a failed experiment. Let me get my pen tool out. It was a failed experiment, but it made people start to question, well, maybe there isn't an ether, a luminiferous ether. Maybe light just somehow travels through the vacuum. Maybe there is not this absolute frame of reference, that's defined by the luminiferous ether. And I want to be clear, it wasn't this experiment by itself. This experiment was one of many that started to put that doubt. But even after this experiment, and they saw that there was no change, no matter how, in the interference pattern, no matter how they oriented this thing, whether it was going in the direction of the hypothetical luminiferous ether or away from it or whatever, when they saw no matter how they oriented it, that they got the same interference patterns, people tried to come up with other explanations that still might have been okay with a luminiferous ether. Maybe the length got contracted in the direction of the motion. Maybe other things got affected. But this is a super important experiment in physics because, once again, it started to show that, hey, maybe there is no luminiferous ether, that light is just going to go through that vacuum, and as we'll see, it's going to be traveling at the same velocity no matter what frame of reference you look at it from. But we'll explore that more in future videos.
What is ether? And you can actually more specifically call it what is the ether. And if we go back to early times, early Greek times, the word comes from Greek mythology, where it was the essence, the air that the gods were breathing. Anyway, Plato and Aristotle used it as they defined the elements, at that time 4 elements. Medieval philosophers continue to use this idea of the ether as a 5th element, and they associated it with the motion of planets, moving around space, and space includes an ether with a known density. By 1687, Sir Isaac Newton published his famous works on gravity, and he used the ether as the medium for explaining how gravity worked. Now, Newton also did a lot of work on light, which has known wave properties, and he used the ether, again, as the medium for moving waves. Now, Newton also did a lot of work on light, which has known wave properties, and he used the ether, again, as the medium for moving waves. But a few centuries later, an experiment was conducted by Michelson and Morley to detect an ether, and the experiment used something called an interferometer. Now, the bummer part about it is it failed to detect an ether. And further experiments, even beyond Michelson and Morley, which also used interferometers to be able to detect an ether, also failed. So it showed there was nothing wrong with the experiment or the apparatus that Michelson and Morley were using. It just said, hey, there's no ether. Which meant by the 1900s, physicists had to conclude that the ether did not exist, and they built particle physics theories without it. But if there's only empty space in the universe, and light has known wave properties, the question is, what is waving? The answer in physics is, all right, light is a particle, it's a photon, but that still is problematic because in that photon there are still wavelengths that describe light and other types of waves. Light has different colors, red versus blue are different wavelengths. So still, even in a photon, something has to describe what causes those different waves and it's a photon. Light has known wave properties. The question is, what is waving? But if there's only empty space in the universe, and light has known wave properties, the question is, what is waving? The answer in physics is, all right, light is a particle, it's a photon, but that still is problematic because in that photon there are still wavelengths that describe light and other types of waves. Light has different colors, red versus blue are different wavelengths. So still, even in a photon, something has to describe what causes those different waves and wavelengths. And every other known wave has a medium. A medium is a substance which allows the wave to travel. A sound wave travels through air, a water wave travels through water, an earthquake, a seismic wave travels through Earth, the material of Earth. We'll get into a little bit more detail here. A water wave is the motion of water molecules, literally H2O molecules. It's a vibrational pattern. And a sound wave is the motion of air molecules. is the medium in this case. Literally H2O molecules. Travels through Earth, the material of Earth. We'll get into a little bit more detail here. A water wave is the motion of water molecules, literally H2O molecules. It's a vibrational pattern. And a sound wave is the motion of air molecules. Air is the medium in this case. And so if every other wave has a medium, we have to ask again, does the ether exist? And if it does exist, why was it not detected in experiments, including the Michelson-Morley experiment? And the explanation starts with this. Right? Shortly after the Michelson-Morley experiment, Hendrik Lorentz suggested that the experiment, the interferometer, failed to consider length contraction. By the way, this is a Nobel Prize winner, and the Lorentz factor later was used by Einstein in relativity, and it can explain length contraction. Now, in the late 1800s, early 1900s, it would have been difficult to build an experiment that considers length contraction, but computer simulations now are able to do it. And what we see here on the left is exactly what Michelson-Morley witnessed. There was no phase detection in the wave, in the light wave for the splitter there. But if you consider an interferometer that is in motion, you do see that phase detection as a result of length contraction. And remember, the Earth is always moving. It's the cause of length contraction is that not only is the Earth spinning, but it's also going around the sun, it's going around the galaxy, but more importantly, it's moving at a very fast velocity in the universe relative to other galaxies. And while that doesn't prove an ether, it could explain why it was failed to be detected. But this is the reason why I am so passionate about the ether is this simple equation. This simple equation in energy wave theory calculates particle energies, calculates forces, but without it, without that one symbol that you see there that is highlighted, everything fails. There are no calculations. It is not possible. It calculates particle energies, calculates forces, but without it, without that one symbol that you see there that is highlighted, everything fails. There are no calculations. The simple equation in energy wave theory calculates particle energies, calculates forces, but without it, without that one symbol that you see there that is highlighted, everything fails. There are no calculations. It is not possible. And that symbol is a density property. And density implies waves that are traveling in a medium. It's a given mass per volume unit. So it's a given mass. And density implies waves that are traveling in a medium. It's a given mass per volume unit. So perhaps there is an ether. If the ether does exist, here's the strange thing about it. More than a century of particle physics has been built on a missing but extremely critical property of the universe. And even this man, Einstein, he was not opposed to the ether. In fact, he's quoted on a handful of times saying that the ether could exist. What is ether? Could exist.
I can't believe it.
What? That promotion gave Kevin a big head?
No, I can't believe how easy it was to save with Geico.
There were lots of things scientists believed a century or two ago that might sound weird to us today. For one thing, they once thought that atoms looked like plum pudding. But over time, as researchers have done more experiments and developed new theories, those ideas have evolved into the science we know today. One of the most game-changing experiments ever was what's known as the Michelson-Morley experiment, not because of what it did find, but because of what it didn't. You see, physicists used to think that all of space and time was filled with what they called the ether, an invisible material that wasn't interacting with anything but was giving light as the Michelson-Morley experiment. One of the most game-changing experiments ever was what's known as the Michelson-Morley experiment, not because of what it did find, but because of what it didn't. You see, physicists used to think that all of space and time was filled with what they called the ether, an invisible Physicists used to think that all of space and time was filled with what they called the ether, an invisible material that wasn't interacting with anything but was giving light its speed. No one had ever material that wasn't interacting with what they called the ether, an invisible material that wasn't interacting with anything but was giving light its speed. Didn't. You see, physicists used to think that all of space and time was filled with what they called the ether, an invisible material that wasn't interacting with anything but was giving light its speed. No one had ever detected this ether, but scientists figured it had to be there. They knew that light acted like a wave, and its speed. No one had ever detected this ether, but scientists figured it had to be there. It was filled with what they called the ether, an invisible material that wasn't interacting with anything but was giving light its speed. No one had ever detected this ether, but scientists figured it had to be there. They knew that light acted like a wave, and waves seemed to need a material to travel through. Throughout the 19th century, evidence was piling up that light was a wave. It reflected like a wave, it interfered with itself like a wave, so it makes sense for light to get around like other waves too, by moving particles back and forth. In ocean waves, for example, the water molecules move up and down, and in sound waves, air particles move back and forth. So it would make sense for light to be moving around something even if it was invisible, and physicists called that something the ether. In the spring of 1887 in Cleveland, Ohio, Albert Michelson and Edward Morley set up an experiment to learn more about the ether by looking for the effects of something called the ether wind. You know how when you try to yell into a particularly strong gust of wind, your voice won't go very far, but if you yell with the wind, it'll go much farther? Scientists assumed that as the Earth moved through this ether, it would create a similar kind of wind. but one that would affect the speed of light from Earth's perspective. So, Michelson and Morley set up beams of light in a way that should have given them different speeds, depending on whether they were traveling with, against, or perpendicular to the ether wind. Then they bounced the two beams off of mirrors so that they eventually reunited with each other, and predicted the beams would arrive at slightly different times since they'd been sped up or slowed down by the wind. But the result? One of the greatest failed experiments of all time. There seemed to be no difference between the two beams. It was like Earth wasn't moving through any kind of ether at all. Over the next few years, physicists tried to figure out how that could possibly make sense. Some said that the experiment just wasn't accurate enough and tried repeating it with better and better equipment, but they still didn't find anything. But eventually, they had to accept that it seemed like there was no such thing as an ether. Instead, light is just different from other waves. Turns out that the speed of light isn't affected by an invisible ether, and light speed through a vacuum is always the same. Space and time will even bend themselves to fit, which is where Einstein's special theory different from other waves. Turns out that the speed of light isn't affected by an invisible ether, and light speed through a vacuum is always the same. Space and time will even bend themselves to fit, which is where Einstein's special theory of relativity comes in. He helped put all these pieces together, showing that physics could work even without the ether. It just meant that completely mind-bending things had to be happening, like time slowing itself down. And unlike with the ether, experiments have shown that Einstein was right. Meanwhile, more physicists were working on some of the other questions raised by the fact that the ether didn't exist. Mainly, if light wasn't like a regular wave, what was it? After a whole lot of experimenting, they realized that even though light did act like a wave sometimes, it also acted like a particle, what's known as the wave-particle duality. It was another brain-melting idea, and one that eventually led to a whole new field in physics, quantum mechanics, the science of the very small. So, the Michelson-Morley experiment might have banished the ether to the history books, but its failure also led to some of the most important ideas in science. Thanks for watching this episode of SciShow Space, and thanks especially to our patrons on Patreon who help make this show possible. If you want to help us keep making episodes
You know what would be great right now? If we still had State Farm.
Could you hit the skip button?
Explain the concept of ether. In the late 19th century, physicists postulated that just as water is a medium for the water waves, and air is the medium for the sound waves, similarly, there should be a medium for light waves too. It was assumed that ether is the medium through which light waves propagate. Ether was assumed to be present everywhere, even in free space. Thus, ether was assumed to be a medium through which the electromagnetic waves propagate. It was assumed to exist everywhere, even in free space. Note that ether had to have an unusual property of being massless but rigid medium. Related term is Michelson-Morley experiment. Question. Remember keywords. Related term is remember diagram. Remember definition. Useful information.
What is ether? There's a lot of discussion about ether exists and ether doesn't exist, and just what is it? And I dug into this question years ago, And I got a pretty good definition, I think will satisfy everybody if they
Alright. Well, that probably works now. So that works now? Yeah, okay. So now I fixed my microphone, right? So I fixed my microphone. But now there's going to be an echo. Right? So I fixed my microphone, and you guys can hear me now. Right? But now when I play this, there'll be an echo. Correct?
What is ether? There's a lot of discussion about ether exists and ether doesn't exist, and just what is it? And I dug into this question years ago, and I got a pretty good definition I think will satisfy everybody if they simply listen to it for a minute or two. So the question is, what is ether? And a lot of people use this spelling, which is ether, A-E-T-H-E-R. In my research, we found out that ether is undifferentiated ether. So this is more like the source of where everything comes from, and ether is a differentiated form, which means it occupies duality, it has motion.
That's fucking interesting. So, so did you guys, can you guys hear me? Please let me know if you can hear me. And how was the video right there? Was it echoing again? I would assume that it's echoing. And you can hear me probably now, right? Oh my god. Alright. Well, that probably works now. Okay. So that works now? Yeah, okay. So now I fixed my microphone, right? Okay, well, I fixed my microphone. And, yeah, so that's not going to work now. Right? Let's see. So that's not working. So my shit really wasn't working? Wait, so how?
Michelson-Morley experiment might have banished the ether to the history books, but its failure also led to some of the most important ideas in science. Thanks for watching this episode of SciShow Space, and thanks especially to our patrons on...
So that was working back then. But I thought my voice was working, but it wasn't the whole time. So let's see here.
Molecules. Air is the medium in this case. And so if every other wave has a medium, we have to ask again, does the ether exist? Its detection as a result of energies percolating.
Yeah, see, I'm trying to talk. I think I thought my mic was working for a solid hour. Yeah, I thought my mic was working for a solid 45 minutes. I was wrong.
Eventually reunited with each other and predicted the...
Physicists postulated that, just as water is a medium for the water waves,
that works just fine. Oh man. Well, I gotta sync that up. Alright, well. Yeah. My video's just not working so well. It's annoying. Wonder why the video doesn't work well. Oh, it's maybe because I have so much stuff up or something? I don't know. Wow. Yeah, it's really... I guess I just have to do a little bit more checking out this microphone.